You hear me? Okay. Oh, I'm trying to log in using my laptop as well because when I do full screen, I'll not be able to see any comments. There are any. So, can you allow me to join? I think.
No issue, sir.
Mhm. I'm trying to share. Do I have rights to share? Okay. Do. Okay.
Your screen is visible, sir, now.
Uh, okay. I'm not able to log in using my laptop. So, uh, okay, we'll check in some other way if there are any comments, and I'll stop if there is any beep. Okay. Yeah. So, good evening, all. Thank you very much for inviting me to take two sessions in this FDP program. And I guess the session is about speech processing, data analysis techniques for speech processing. Speech comes from audio data. So my work is mainly related to audio analysis. But the challenges that we will discuss today, challenges, solutions, and underlying techniques that we will discuss, may apply to speech processing as well. Like this concept drift, it's a challenge which is emerging these days in research community, especially machine learning, deep learning community, because the models which work right now very efficiently, they may stop working very soon because of concept drift, and we'll see various examples of concept drift what it is. But it so concept drift challenge is very difficult to handle, and for supervised classification, like for binary classification, uh, uh, there has not been much progress in concept drift, handling concept drift. But in case of anomaly detection, some researchers have made some progress. In our lab also we have done some work on handling concept drift, particularly for anomaly detection problem. And in case of anomaly detection, this concept drift makes more sense also because there are two classes, and one class has heavy concept drift, whereas there is interclass as well as intra-class concept drift. Now, I was told that there are participants from uh, participants from computer science as well as other domains. So I'll go slow. I'll explain some basics as well to the audience. But still, if you have any questions, it will be better if you ask questions because I would not know all background context of all the audiences, and it's good if you understand what I'm telling you, and that will only be possible if you ask, and I only tell those things which you are curious about. So uh, please give me please give me one just 1 minute. Sorry for the interruption. some noise at home. So these are my qualifications. Already told briefly. I am Bachelor of Engineering from Rajasthan University. I worked as research associate in IIT Bombay for some time. I did my master's from IIC Bangalore in electronics design and did PhD from Singapore. After that, I worked for a few years in Canada, in University of Winnipeg and Ottawa, doing postdoc, and worked as postdoc in New York University as well. Finally, I joined IIT Roper Computer Science Department in 2016. Since then, I am here. My research area is multimedia analysis. Basically, we try to extract semantics out of text, audio, video, images, all these modalities, and we try to combine all multimodal data in order to build some systems like multimedia systems, automatic movie making, or video surveillance systems, or multimedia for teaching in classes. Okay, and here, so so in order to understand the challenges which we handled and how we have handled, I will start with anomaly definition. So because we have addressed this challenge of anomaly detect this handle this concept drift challenge specifically for anomaly detection problem. We'll start with anomaly detection. Now, anomaly detection finds applications in all domains, and speech processing, audio processing, everywhere, and which you will come to know in a few slides itself. So anomaly is there are many definitions of anomaly in the literature. So basically, it's something rare in your data set. Anomaly, you are given a set of data points, and you have to identify a data point that is significantly different from the rest of the data points. It's like this. Suppose you have uh, audio data, a speech which some prime minister has given. Now you take all the sentences, and from in all those sentences there is one forgery. Somebody has inserted 1 second of audio in that. Now, except that 1 second of audio, rest of the audio is spoken by one person. So it is generated by one source. So if you look at its properties, those properties will be uh, they will represent that one person. But this one sentence, if we are able to model properties correctly, this one sentence will differ significantly from others because it is spoken by some other people. So now this rareness we can find by using audio processing, which we do, like taking audio clips and converting into small windows. For each window, we calculate some features and we analyze those features. It can also be done using speech processing, like you can convert data to speech, and speech can be represented using bag of words, using natural language processing techniques. And see, if you read an email, generally you find out whether it is written by the other person or someone else. Like I'm a faculty at IIT, get emails from students. Sometimes students' parents email us on their behalf, but they don't mention explicitly, and we read the email and we find out that the email is written by student's mother or father, not by the student. Because the student generally makes a few mistakes, generally has some styles where it is not formal. All this information is available in rest of the emails which are sent by the student. So from rest of the emails, we create some kind of model. That model is like normality model. And by using rest of the data, we have to find out a given email whether it is written by student or not, whether it is anomaly or not. Is it conform to rest of the data? So that's anomaly definition. So here it is apparent that in order to detect anomaly, you need to have rest of the data as well. Anomaly detection has I mean, there are enormous number of behavior applications. Uh, these days, we have uh, this mental health of individuals is deteriorating due to COVID and due to job scenes, due to various family pressure. It could be for any region. And we are at IIT here. Students, they sometimes they feel a lot of peer pressure studies because all the students are toppers of their schools or their states. They come here, they compete with each other, so their mental health goes deteriorates, and their behavior becomes different. For instance, there is a comedy show going on. All others would be laughing, but one person would be sitting with a very serious expression. That person is anomaly. If we have automatic systems, we can detect that. And same thing applies for emails and audio communication as well. The kind of words a person uses, the kind of sentences a person uses, it does change when the mental health is not sound. So, uh, uh, anomaly detection is used in mental health analysis. And it is used for data cleansing. Data cleaning, and here I guess even if you are using speech processing, uh, for any speech processing model that you use, there may be some noise points or some exceptions. Those noise points, if you remove from data set, your model will perform better. So in that this topic comes under data mining. You do pre-process your data in order to improve the quality of data so that you can do better modeling. For example, I have this Siri which detects my sound. This Siri it detects my sound, my command on my phone, but when I was training it for the first time, there were kids around me and they also started talking to Siri. So Siri got confused, and initially when I used, could not recognize my sound. It could not recognize my comments, and that was because the model which was trained had noisy data. So this anomaly detection can be used for data cleaning. For example, this is a data set from for face detection training. I have a model which I want to train for face detection, human face detection. In this, you can clearly see there is an anomaly. So this is anomaly. So if you get rid of this anomaly, then your algorithm will do better. Your models will be trained in a better way. So this is anomaly detection problem. Let me give you a simple example. Can you look at this data and like give me some hint on this is height weight data of 50 students, 50 persons. Can you tell me what is anomaly? I mean, which student is anomaly? There is one anomaly at least.
The third student, uh, 8, third 1, 4, 7. So third student.
Third student height is excessively large.
Yeah.
Oh,
And
but
also
it's
the 15th. 50th.
50th.
Yeah.
Okay. Yes, I mean, here we have looked at just one weight parameter, and the weight is very large for two students. But if you look at weight and height together, then we can determine it better. So this student, so this is weight and this is height. So I have made a scatter plot. So in this scatter plot, it is very clear that this student is anomaly. This dot. This is anomaly because it does not conform to rest of the data points. The height weight plot, and it gives me an idea that if I calculate height by weight ratio, then it is going to be around some average value. For most of normal people, it is going to be around some average value. But if there is one person whose height is very low, like whose height is 4 feet, but whose weight is 100 kg, that person's height by weight ratio will be significantly different from others. So it is here. Like most of the height by weight for my given data set is around 1. For one student, it is significantly different. This is student number 14 or something. So also here, we can talk about the first way of detecting anomaly. Here, this data, which is around 1 height by weight ratio, this we can model, and we can create a model, and for any data point we can calculate what is the probability of generating that data point, what is the possibility of this data point, red one, being generated by that model. The possibility is going to be very less in this case. Okay, so we have height by weight ratio. Now again, I'll ask a simple question here, that we intelligently could come up with this height by weight ratio, which we expect to be around some average value for normal people. We expect it to deviate significantly from this normal for abnormal people or anomaly. How much deviation is sufficient for calling a point anomaly? We encounter this situation very often in normal life as well, where we expect things to be around some average value, and if a thing significantly deviates from that average value, we call it anomaly. जैसे क्लास में आ रहे हैं 1 or 2 minutes later तो okay है, but if some student is late by 10 minutes, then we call it anomaly, we penalize the student. But so that is, we in practice we do that. But if we use computers, we have to find out how much deviation. We have to come up with a static rule, and that rule, we one thing we can do is we can observe data for a long time and manually set that threshold. That if deviation is by more than 0.5, then it is an anomaly. But we don't do that. We have a very powerful method which is called Z value test. And this Z value test, it says that for all data points, you calculate that Z value. Okay, so let me explain what are the things here. Here I am calculating Z value of each of these. Suppose I had all these data points, students, height by weight ratio. I have to calculate Z value for each of these. And in order to calculate Z value, I use this formula. Zi is for ith data point, xi is height by weight ratio, and I have two parameters, mu and sigma. Now mu and sigma, these are my model in this case. So what is mu? Mu is just the mean value of height by weight ratio, which we generally use. It would be 1, I think, for the given figure. In addition to that, we also use one other parameter. It is called standard deviation, which is actually square root of variance. And that variance is calculated with the following formula. We have n is number of samples, xi is individual data point, ith data point, and mu is mean. So basically, We are calculating variance. We are calculating how far each data point is from the mean, and that is calculated, that is captured by this standard deviation. So this standard deviation, it captures spread of data. We have to model that spread also. क्योंकि in the image, in the graph which I showed you, values were around 1, but it could be the case that there is some other country where it varies between 1 and 2. In that case, its standard deviation would be higher. We have to take into consideration that while calculating anomaly. Calculate Z score. Now, higher Z score will indicate that the data point is anomaly. There is a rule of thumb that says that for Z value greater than or equal to 3, it is an anomaly. And that rule of thumb generally works. So this is better than using a threshold by observing the data. And it generally works because of one reason. That reason is Gaussian distribution. Most of the variables we encounter in real life, they are Gaussian distributed. Gaussian distributed means they are around mean. And if a variable is Gaussian distributed, then the probability of that variable having or taking a value more than mu plus minus 3 sigma is less than 1%, which is a property of anomaly. Anomaly is a data point with a very, very low probability of happening. It's a rare event. So rare, by rare we mean rare is something whose probability is very less. It's like raining. I cannot say rain. It can rain anytime, but it is like snowfall in May in Rajasthan. Very, very rare event. The probability is not zero, but very, very close to zero. So that's an anomaly. So therefore, if you take a threshold of mu plus minus 3 sigma, like if Z score is more than 3 sigma, then that's an anomaly. And in this, what we have done, we have used two parameters. One is sigma, other is mu. And these two parameters combined, they represent our model. In this model, what are we doing? We are actually learning the distribution of normal data. All classification analysis modules, eventually they learn probability distribution. Joint probability distribution of all the variables which are known and which are unknown. So in this case, we are learning the distribution of normal data, and we are assuming
Sir,
that the
slides
normal
are
data
not
is.
visible. Pardon, sir. Sir, your slides are not visible.
I mean, are they not visible since beginning or now?
No, just now, just
Sir,
now.
just now, sir.
Just now.
Okay. Let me share.
So now visible, sir. Everything is fine.
Okay. I'll do it again. So this is typical anomaly model. In fact, I was telling about general data analysis. We learn distribution of probability distribution of class, all the classes like class 1 and class 2, using the probability distribution given the
Sir,
variables.
pardon, sir.
Yes.
Sir, please restart from that Gaussian distribution page. Lost the
Here.
connectivity. Yes, sir. Sir, from this page. Thank you, sir.
Okay. Here, I was telling that the probability of a variable having value more than more than 3 sigma is less than less than 0.01, which is definition of anomaly. Like here in this model, we have assumed that my data is Gaussian distributed. My normal data is Gaussian distributed. Now Gaussian distribution has two parameters, mu and sigma. And Zi, it is telling us how many sigma far this xi is from the mean value. If Zi is 3, then we can say that this any data point is 3 sigma away from the mean value. And if a data point is 3 sigma away from the mean value, the data point is very likely to be anomaly because the probability is very less. So this is probability, Gaussian probability density function. And here this mu has the highest probability, and the probability decreases as the distance from center increases, and at 3 sigma it becomes very low. So therefore, all the data points with Z value of more than 3 sigma are anomaly points. So this is Z value test for anomaly detection, and it can only be done for univariate data, where data has just one variable. So with this, I'll just describe typical anomaly detection models. In typical anomaly detection model, we take the dataset, full dataset, and from that we just learn the normal distribution. Now this dataset may contain anomaly also, but like in our previous example, we learned mu and sigma. You can see anomalies are less than 2% or 1%. These 2% or 1% data points will not affect your mean because 99% are anyway normal data points. 99% of persons have this height by weight ratio of 1. So this model will have normal data characteristic. Ideally, we should try to get normal data itself in order to learn this normal model. But sometimes we may not have labels for the data, whether this data is normal or anomaly. In that case, we take the whole data and try to learn a model from that, and we assume that everything is normal. Because majority of the data points are normal, our model will still do better. But in some cases, wherever possible, we take normal data set. For example, I was talking about behavior analysis. It's very hard to get a person who is sick, and because of ethical reasons and permissions, we can't take that data also. But there are a lot of healthy people, so we can take audio of a lot of healthy people, and we learn some models, and we say this is normal model. We take whenever we are applying that system for classification or analysis, we can take that model and take the input audio, try to calculate what is the how much does this new sample fit our model. If it doesn't fit, we say it is an anomaly. If it fits very well, we say it is normal. So this fitness again for my other colleagues who are not from computer science, this fitness is calculated using probability. So it's like this. We have, suppose we are given this vector. This vector is audio data. Let me take audio only. Audio, 1 second audio. We have a model, probabilistic model. We calculate probability of, given the model, generating this audio. This probability is also called likelihood of generating this data given the model. This probability will tell us whether it is normal or not, because if model is trained on my sound and audio is also of my sound, my speech, then the likelihood will be very high. However, if some other person is talking and the model is trained on my speech, then the probability will be very low. So a low probability here indicates that it is an anomaly. We learn the model. Generally, these are probabilistic models, and we have a data point. We calculate deviation in terms of probability, and that probability we can manipulate this probability to calculate anomaly score. For instance, in this case, I can take 1 by p as anomaly score, because when p is high, anomaly is less. When p is low, when the probability is very, very low, anomaly is high. And based on that, I can calculate whether it is normal or abnormal. So all anomaly detection methods, they model normal data. They learn distribution of normal class. And now we discuss the challenges in anomaly detection. One of the challenges in anomaly detection is high intra-class variance. Uh, it's like I gave you an example of my sound and some other person's sound. Somebody may argue, people who are working in supervised machine learning, they may argue that why don't you collect data, lot of data which represents anomaly, lot of data which is normal, and you train a binary supervised classifier. You may have heard of deep learning models that are very good in supervised classification. You may argue that. But the problem is high intra-class variance, due to which we cannot apply those models for anomaly detection. And what does it mean? I give you an example of my sound. My sound is normal sound. For my anomaly detection model, my sound is normal. I can talk for hours, I can collect data, that becomes my normal sound. What about anomaly? Anomaly could be sound of my daughter, sound of my wife, sound of my students, and all other people in the world. Therefore, this anomaly class has really huge intra-class variance. There can be really so many different type of people or data points that can be there in anomaly class. So therefore, it is very hard for supervised models to detect anomaly or to model anomaly. And for the same reason, this anomaly data is not available easily. Simple, like for healthy and sick person, this sick person's data will not be available. I mean, you will not have access. Even if you have access to hospitals, abnormal behavior, those patients are very rare. So you installing cameras, audios there, it is prohibited. So it's very hard to get anomaly data. Yes, there was a question. Question. Audible?
Yes, sir.
Yes, sir.
Okay. कोई क्वेश्चन था क्या अभी?
No, sir.
नहीं था. Okay. We'll go ahead. We'll connect it with our main topic as well very soon. In anomaly detection, availability of data is a big challenge. Anybody is looking for research problems or doing research in audio processing or machine learning, these anomaly detection and concept drift, these are very hot topics. In those topics, you can find some interesting problems. Anomaly is
Actually, sir,
context dependent.
yes. At this moment, anomaly, we are using new word anomaly and abnormal data. Why this new word? It is like abnormal things, abnormal data or abnormal interrupt, something like that.
Mhm.
In
So
this sentence,
anomaly,
new word, a new word. Normally, we are using. Is there some specific reason or this specific word is normally we are using?
no specific meaning. We work in multimedia data analysis. For hardcore mathematicians, they may have different meanings. For multimedia scientists, for us, anomaly and abnormal are same. So we say anomaly. So abnormal and anomaly we use synonymously.
Okay, I got it. Thank you, sir.
Abnormal has more semantic meaning, so we sometimes use that word. Oh, sorry for not explaining that in advance. So here, anomaly or abnormality, this has context dependency as well. For instance, you have this uh, person running on road, person running on running track. Both of them are doing same activity, but this one is okay, this one is normal, this one is anomaly. Fighting in garage is abnormal, anomaly. Fighting in this ring is normal. So whatever model we are using, that model should learn special context. That in this context, people are supposed to run or fight. Temporal context is also very interesting. You know, so if you have such waveform, you show this waveform to your doctor, and you say this is my some physiological parameter. The doctor will say that this both this point and this point they have same value. You know, if you map them to x-axis, the exactly same values. But this one will be called anomaly. This one will not be called anomaly because there is this concept of continuity. This one is the first one is continuous, but the second one is there is some abrupt change. So it depends on temporal context that it is supposed to follow some path, but it is not following some path. So our anomaly model should learn temporal context as well. And the title of our discussion today is online anomaly detection, which means we will be detecting anomaly in time series data. So we'll start with non-time series data, and then we'll discuss time series data. And finally, the concept drift. In fact, all other concepts also, they are more or less related to concept drift. Because of this, this problem becomes very challenging. We have done some study on concept drift in audio analysis as well, which we'll explain later on. For now, let's just see what is concept drift. I told you that I have mu and sigma, which I have learned my data set, and that the data set represents normal data. This mu and sigma, they represent my normal data. Normal is my class, so it is my class distribution. So in mu and sigma, I have learned the probability distribution of normal class over input variables. When I do binary classification, multi-class classification, if I have 4 classes, then also I learn probability distribution of each of these classes given the variables. So if there are 2-dimensional variables, for some values of those variables, probability will be very high. So I'll have to learn this distribution. All your machine learning models, including deep learning models, they indirectly or directly learn these probability distributions. Now, this probability distribution may change over time, especially in case of anomaly detection. Happens very often. For example, these 2 images I have taken from this city. What was this city where Corona started? In China. It's sorry, I forgot just name. The coronavirus originated from one city in China, right? So in that city, this was normal traffic during afternoon. But when Corona happened, this was normal traffic. If you have placed any audio or a microphone or a camera, in both cases, this you must detect that this is actually normal class. This is not anomaly. In Corona time, if there are a lot of cars, it is an anomaly. There is one car, it is normal. What has happened is my normal class distribution has changed over time. This is called concept drift. Over time, class distribution changes. Mu was supposed to be at like 0.7, but because of corona, it has drifted to 0.4. You can see that if we have some machine learning models are trained on data today, which are being used, if this concept drift happens, those models will not be useful. In case of anomaly, it happens very often that our normal class distribution changes. You can think of audio surveillance as well. In case of audio surveillance, at afternoon time, the audio noise in the surrounding, it will be large. That is still normal. We'll still try to detect a gunshot. At night time, things become very quiet, so the normal itself changes. The normal distribution changes. So if I'm using a single model for doing surveillance using a microphone, that model should understand that there is concept drift in my normal class and should try to take care of this concept drift, which is very challenging. We have made some attempts to do that, with some results I will also share with you, and some standard model for handling concept drift also we'll discuss. So the concept drift can be of two types. One is intra-class. Now, intra-class concept drift is what we have been discussing so far, that I have normal data and this normal class itself is changing over time. Sometimes we have inter-class data, inter-class drift. Inter-class drift is literally this example. This bottom image, it was abnormal before COVID. It became normal after COVID. You can see this data has jumped from one class to another class. So this is called inter-class drift. Both the drifts we have to study. Now, one of my students was working on using audio for cattle surveillance in farms. We are doing a lot of projects to help the farmers at IIT Roper, and the farmers requested us that, sir, can we have something that can help us detect whether there are animals invading in our farm or not, because they cause a lot of damage to our crop. So we thought of using audio sensors, because that's how we humans also, we hear somebody entering our house or a farm. So we thought we'll install an array of sensors, microphones, and we'll detect intrusion. And we started developing models, and we could not do anything. In fact, even now we are not able to do much because of concept drift. When the wind starts blowing, in microphone you get a lot of sound, hissing sounds like that. But when the wind stops, this whole sound is gone. During the night time, morning time, afternoon time, this normal class itself changes. So here what we are doing, that we were trying to learn the normal sound in the farm, and anything abnormal will detect it as intrusion. And that has come from human experience. By talking to the farmers, they say that we are sleeping in the farmers, we hear bird sound, we hear different sound of my pump and all. But when cattle enter, they break our crop, so there is a different kind of sound. So sometimes we recognize using sound analysis, sound by hearing sound. And initially, when cattle enter the farm, the sound will be very different from other sounds. So we are using anomaly detection for that. But we could not do anything. So what we did, we further tried to study effect of concept drift on this problem. So that's where we are right now. For that, we collected some data set. We put a sensor in the center. We walked around the the sensor at different locations. Our goal was to identify whether some person is walking around the sensor or not. If somebody is walking, then it's an intrusion. Otherwise, it is not intrusion. And we collected data on 2 dimensions. We collected data at different places, like 2 different places, and at 2 different times also, in order to study the effect of this concept drift. This is the simple model that we use in order to detect this intrusion on this collected data. Here, our goal was not to make very accurate classifier. Our goal was to study the effect of concept drift on audio analysis task, because we did realize that in case of audio, this concept drift is very prevalent, and a lot of researchers who are working in audio related research, even the speech processing, they're kind of ignoring this concept drift. If we can handle this concept drift, the models will become better. So we have input files. We collected some files were in WAV format, some files were in MP3 formats. We so like we had 1 hour of audio, but we cannot analyze 1 hour of audio. We have to divide this audio into small chunks. We divided this audio into small windows of 1 second, or in fact, I don't remember, 1 second or 4 seconds. So we took 4-second chunks, and we converted those into a spectrogram. Is there anybody in the audience who knows what is a spectrogram? Okay. So spectrogram is representing any time series data in terms of in terms of time and frequency combined representation. So what we do, we take small portions of data and we detect its frequency. Suppose there are F1, F2, F3, F4. 4 frequency components we extract using Fourier transform or Fourier series, any frequency analysis method. At t equal to 1, we measure their values 9, 8, 7, 6. At t equal to 2, they have different values 18, 24, 7, and 8. At t equal to 3, there may be some different values 20, 15, 16, and 2. So these values, you can assume these values to be pixel values and create an image. You know, our image is 2-dimensional matrix. It has certain pixels. When we go to buy a phone or a camera, we look at pixels. How many pixels?
Excuse me, sir. Is there any rule to decide the size of chunk of the data, like 1 second you said, or 4 second, or 2 second? Is there any rule to decide the size? Because accordingly a spectrogram will be changed.
Yes. That rule depends on your end application and your class. If, like in our case, the class was to detect intrusion, for that we had to capture at least 1 or 2 steps of a person who is walking. So in less than 1 second data, we may not capture the step. But if we take more than 1 second data, we'll at least capture 1 step of a person who is walking. So because of that application, we choose this window size. So the rule is simple. The rule, the window size should be as small as possible, but it should capture your class properties as small as possible, because the annotations which you will get on your audio, they will be very fine, and fine information is always good. It is desired that we can label each individual second or microsecond of audio. But if you take 1 microsecond of audio, that audio may not capture the class. In our case, the class was a walking person intrusion. So you do experiments whenever humans are involved, then it remains around 1 second. So that's how we chose the window for machine learning model.
Okay, thank you, sir.
After we so this we converted data into frequency and temporal representation. So this one is called spectrogram actually. If you assume these values to be pixel values, this becomes an image and it's a spectrogram. So that's what we get here. Once you have the spectrogram, then spectrogram is literally an image, but its values are actually frequency amplitudes of these different components. So once you have the spectrogram, you can use all your machine learning, deep learning models, which are popular for image analysis. So here we have explored EfficientNet, CNN, VGG16, 19, LXNet, ResNet. All these are machine learning models for image analysis. And after using these models, so these models are they're very complex but very easy to use. There are some Python libraries. You can just write 15-20 lines of code in order to build a classification model that takes images. But the key part here is you have to give images of both the classes, when the person is not working, when the person is working, like intrusion and normal. And finally, we calculated the performance, and these were the results. Here you can see what we did. All these models, we first tried effect of location. We trained on one location, and for I'm talking about this experiment, we trained on one location and we tested on the same location, like near the hostel, and we got good accuracies. But when we trained on one location and tested on a different location, the accuracy reduced significantly. For most of the models, accuracy reduced significantly. And so this is very important, because if you are trying to build an model or machine learning model, and if you're trying to sell it in the market, you cannot make a model that works only in Roper. But if you take it to Jaipur, it will not work. Models should not be like that. But in case of audio, this problem happens that because of the concept drift, a model which is trained on one location may not work as efficiently or as accurately on other locations. We studied the effect of time as well. Like here we have 4 different types of experiments, same time and same location. We got good results here, but same time, different locations. Like in same time means in the daytime itself we recorded, but we changed the location, accuracy reduced. Same location, but different times we tried, then also accuracy reduced. But the worst results we got when we use different times and different locations. So here our
Sir, what are
conclusion
these
was
values in the data?
these are
Please-
accuracies.
Sir?
Accuracy in percentage.
Yes, sir. Okay, okay, accuracy.
It's a binary classification, so we can take accuracy.
Okay, sir. Yes, sir. Yes.
We concluded that in case of audio analysis, class distribution suffers from massive concept drift and with spatiotemporal variations. And if you train model once, it may not work in other environments. There is a need to develop adaptive models. And we have developed some models for anomaly detection, adaptive models for anomaly detection, which we will discuss. Can we take a break of 8 minutes, like 8:10? Can we start at 8:10?
Yes,
Yes,
sir.
sir. No. Yes, sir.
Okay. My throat is dry now. I'll go and have something to drink.
Oh,
Yes, yes.
Okay. I'll see you at 8:10.
Dear participants, you can also take the drink break here. After 10 minutes, sir will continue. If you have any question, you can write in the chat box. Sir will answer first. After that, we will start the second session. If you have any doubt regarding FDP, you can also ask the same from me.
Can we start now?
Yes, sir, we can start, sir.
Okay. So now I believe now you have a pretty good understanding of the term concept drift and how it affects audio analysis severely. We are trying to address this concept drift challenge both for anomaly detection as well as supervised binary classification, like the intrusion detection what we discussed. But for binary classification, we do not have much success. But for intrusion, for anomaly detection, there are some standard methods which we were able to use. So we'll start with basic anomaly detection in order to understand how these methods are used. So we'll start with anomaly detection using clustering algorithm. Clustering algorithm is when you are given data but you know nothing about the data, you have to divide data into different clusters. These clusters you can find these clusters based on many different parameters. For example, here I had these 15-20 balls, and I have clustered them into three types of balls. One is blue, other is green, other is gray. So like this kind of clustering, it's just a core of data mining subject, and it is very it's useful for classification as well as anomaly detection. And there are many other applications of clustering as well. If you have audio samples, like in one of our work, we were trying to detect whether a student is talking or a teacher is talking. We took the audio samples of the whole class, but all the audio samples were clear. Like whole when the teacher was talking in microphone, student was also talking in microphone. The same is true for this online class as well. And our challenge was how do we identify which one is teacher and which one is student and which are how many students are there. We just had audio samples. I mean, we could hear and we could find out that this is student 1, this is student 2, this is student 3, this is student 4. And we could count number of students, and we could also find the teacher by listening, by looking at the way, the kind of sentences being used. Because teachers' sentences will be mostly descriptive, the students' sentences will be mostly interrogative, like questions. But if you cannot hear that, if you want to use computers to do that automatically, we did. In fact, that was one of our published papers. We divided this whole audio into small chunks of 1 second each. Again, 1 second each, or I don't know. Let's say it is 1 second each, and for each 1 second audio, we converted that into a feature vector. For that, we use MFCC feature vectors, and we try to cluster these data points automatically. Now, all the if there is one teacher and 4 students, we got four clusters, like 5 clusters. So data points were naturally in 5 groups, 4 and 5. And out of these 5 groups, there was one group which had a lot of data points. So that was teacher, all others were students. That way, clustering is very useful when you don't have labels of the data. In the given case, where we are trying to detect anomaly, we have height by weight ratio of all the students, but we don't have labels. Which one is anomaly and which one is normal? Our goal is to find out anomalies automatically. even we are using it for data cleaning, at that point also, if we already know which one is anomaly, we don't have to use this method. We are given the whole data set. We don't know labels. We have to find out these labels. Which one is anomaly and which one is normal. So here, given set of data points, we can divide that into clusters. And the way we find these clusters, that relates to anomaly detection. And that relates to concept drift also later on. We'll first discuss this, how we find clusters in a how do we find clusters in a given set of, like cluster centers in a given data set. Let me see if I have. Okay, I'll go to. Okay. So, okay, we'll discuss here itself. I'll use the bottom part of the slide. Okay, so clustering is an algorithm where we are given some data points. And we have to automatically find out that this is one cluster and this is another cluster. And we have to find out their cluster's mean vector as well. This process is called clustering. So here there is a very famous algorithm goes. We can randomly assume that any two data points, let's say this data point, and this data point are two clusters. You can initially assume that. With this assumption, I could not listen to the question. Sorry, it was broken. Maybe. Hello. I mean, can you type your question in the chat box, please? I only see one message, not audible.
Sir,
Is
please
like
continue, sir. Sir, your voice is clear,
was
sir.
it
Please continue, sir.
okay? So I start with assuming that these are my two cluster centers, and the rest of all these data points, I start assigning them to one of these clusters. So this may be my cluster 1, this is my cluster 2. So I start giving labels to rest of the data points. So this, whichever center is closer, I'll assign C1, C1, C1 because it is closer to C1. This will be C2, C2, C2. All these are C2. Most of them are C1, some of them are C2. So the points will be labeled like that. Once the points are labeled like that, what I will do is for each cluster K, for C1, cluster C1, all the data points which are labeled C1, I'll calculate their mean again. All the data points which are labeled C2, I'll calculate their mean again. Now in this image, you can see that this C2, which was initially here, most of the C2 points are in this region. So mean will shift to this direction. This mean will shift to this direction. Slowly, so after the means have shifted, so this is new mean, this is new mean. You repeat the whole process. You try to label all the data points again. And slowly, it will and go to the center of this cluster. Basically, your end of this Linde-Bujo-Gray algorithm will be your cluster centers. This your cluster centers I'm marking in green. They will come very close to actual cluster center. This is called Linde-Bujo-Gray algorithm. Now, I have a question now. When do we stop? So, like my mean has moved. I can again label these points. Once I label these points, I can again calculate the mean. My mean will be updated, and I'm telling you that as we keep updating this mean, it is going towards our global solution. It is going towards our actual mean. We have to stop somewhere. This is computer. We are not monitoring it. We cannot see it. We have to have some rule which we can write in our Python program, and that says that you can stop now. Intuitively, like based on common sense, when should I stop? Okay. So this solution is moving. Initially there was huge movement in my mean value. My cluster centers, it changed drastically. But let's say my actual mean is 0.8 and my estimated mean was 0.4. It became 0.5. Eventually it will come to 0.79, then 0.799, then 0.7999. If it is not 0.8, it will be very close to this one. When in some iterations, if I do realize that my mean is not getting updated, then I can stop there. I can assume that I have reached very close to my actual solution. That is stopping criteria. Now I have another question. I may have two algorithms. One algorithm is giving me these two mean values. There is another algorithm that is giving me these two mean values. Okay. Which algorithm is better? The algorithm that gave me blue ones or the algorithm that gave me green ones? ये तो हमको समझना पड़ेगा, वरना आगे तो फिर कुछ समझ ही नहीं आएगा हमको. Intuitively, which one looks a better algorithm? The green one looks better algorithm because it is giving us actual center of the cluster. Blue ones are at the corner, at the edge point of the cluster, so they are not good in vectors. This is not a good clustering algorithm. These cluster centers are not good, but this green ones, they are good cluster centers. And the green one is good because if you calculate distance of all the data points from this green cluster, from this green center, this distance of all the data points you calculate, you add all this distance together, it will be more for green data point because most of the points are very far from the center. Whereas in case of green, most of the points are close in nearby vicinity. But in case of blue ones, only few are close to it, but most of them are far. This is actually called distortion of a cluster. Distortion. Distortion is mean distance of all the data points from cluster centroid. The cluster is not good, distortion is high. When the cluster is such that data is spread in large area, then also distortion is high. So in a way, a clustering algorithm is good if it gives us minimum distortion. For a given number of clusters, like we have 2 clusters, we divide data in such a way that the distortion is minimum. And that will be minimum only for this green case, it will not be minimum for blue case. Okay, so now we move on to anomalies. We had some data points. We took these data points, we divided into clusters. So these are data points. Maybe I'll make one more cluster. This is cluster 1, this is cluster 2, this is cluster 3, and this is cluster 4. I took data, I could divide into different clusters. Now, this is the question, which cluster will have anomalies? Now, I have all data points, they have one label. The label is either C1, C2, C3 or C4 depending on our clustering algorithm. My question here is, which out of these 4 clusters, if I am saying that one cluster has anomalies, which cluster will it be?
C4
C1,
should have.
it will be C4. And if we talk about statistical properties, C4 has some data points, let's say n data points. So what statistical properties will this C4 have if it has anomalies? Can we talk about distortion? What will be the distortion of C4?
I think all the points in the cluster C4 as compared to C1, C2, and C3, the standard deviation, variance, skewness, kurtosis, all this statistical behavior will be anomalous type.
Actually, mostly the distortion will be distincting features in case of C4 for anomaly detection, because we discussed earlier, anomaly has large intra-class variance. So C4 will have very small number of data points, but distortion will be very high. Distortion will be very high. I'll say average distortion, because in case of all other C1, C2, and C3, they do represent our normal data. So the data will occur in density. There will be a lot of points near to each other, but C4 represents anomaly. If C4 represents anomaly, anomaly has a characteristic of high intra-class variance. And variance is nothing but distortion. So if we calculate average distortion is going to be high for C4, whereas it is low for C1, C2, C3. So average distortion and size in terms of number of data items. So for a cluster represent anomaly, its size will be small I mean, number of data points will be very small and its distortion is going to be very high. So in fact, we use it in reverse order. We take input data, we do clustering, we find all the clusters, all those clusters, for all those clusters, we calculate distortion, we calculate their size, we calculate ratio of distortion and size. Based on this ratio, we determine whether a particular cluster is anomaly or it is normal. For that, we can assign some threshold again. But assigning threshold for that is relatively easier. So this is when we have a cluster as an anomaly. Suppose this does not exist, C4 does not exist. I don't know how to erase it. Suppose C4 does not exist. I only have 3 clusters. And somebody told me that there are anomalies in your data set. These anomalies are in isolation. They are individual anomalies. They don't belong to any clusters. So how do I use this clustering result in order to find anomaly score for all the data points? Because I need anomaly score for all the data points in order to find out which are anomalies. The data points with high score will be anomalies. So other approach we can use here is data points which are very far from center. They may be anomalies. So distance from center we can use as anomaly score. Because anomalies are going far at the periphery. Because we know anomalies do not conform to any other type of data points, but they are in isolation. So they will try to get inside one of the clusters. But still, they will be far from other data points because we know it is an anomaly. There cannot be any other data point nearby. So if we take inverse of distance from center, actually distance from center, this is also anomaly score. You see. Okay, now when we have these clusters, it gives us opportunity to use a probabilistic model also, Gaussian mixture model. Maybe okay. We have that later on. So that's how we use clusters for anomaly detection. Let's move on to the next actual topic, which is online anomaly detection in time series data. So here the two examples of anomaly detection. We can do point anomaly in case of time series data where we discuss a particular sample value as anomaly, and sequence anomaly. Generally we encounter sequence anomaly in multimedia case. We take that's why we take a 1 second sample. In that 1 second we try to see the sequence of samples and we try to see whether there is an anomaly or not. And as we discussed, one of the main challenges in anomaly detection in time series data is concept drift. And in order to address concept drift challenge, we need to use adaptive model. And the moment we talk about adaptive models, we have to go to probabilistic models, because in case of probabilistic models, our friends in mathematics community, they have given nice tools to update various parameters of mathematical models, especially probabilistic models. Your deep learning models are not probabilistic models, so you cannot update their parameters the way you can update your probabilistic models. So we have to use probabilistic models. So we already discussed about clustering. You remember we had three clusters. We had one cluster. We had three clusters. Now we can use this information of clusters to build a probabilistic model, and we will actually use Gaussian mixture model for that. We'll assume that there is the data, normal data consists of three Gaussians: Gaussian 1, Gaussian 2, Gaussian 3. Each of these Gaussian distributions will have their own corresponding mu and sigma. And depending on number of points in each of these clusters, we'll have some weights also. Weight is actually nothing but fraction of data points that fall in each of these clusters. So we have our whole data we have modeled as a GMM, Gaussian mixture model, which basically it represents these three clusters. And in these three clusters, from these three clusters, we have obtained mu, sigma, and rho. So mu, sigma, and W. And by using GMM equation, we can calculate. So we can calculate probability of any data point. So this is equation of Gaussian mixture model. K was 3 in our example. We obtained three weights. Weights were fraction of data points in each cluster, and we had mu1, mu2, mu3, and sigma 1, sigma 2, sigma 3. In fact, this is sigma when we have multivariate data. Multivariate data is when the number of variables in the vector representing a data point is more than 1. If it is 1, then it is univariate data. In case of univariate data, we can use sigma. In case of multivariate data, we use this capital sigma. I think this is also sigma, but it's capital sigma. And this fx, it gives us x is a data point for which we want to find out whether it is anomaly or not. Fx gives probability density of x given our Gaussian mixture model, which consists of three Gaussians. This is the formula for that. For these weights actually this should be Wk. Weights are between 0 and 1, they sum to 1, and this formula, by using these weights and weighted combination, we calculate probability density, and that probability density, inverse of that probability density, we can calculate, we can take as anomaly score. Is when inverse of probability density can be used as anomaly score. So again, I can just repeat this, that we have GMM. GMM is a probabilistic model. If you don't want to understand any of these variables, parameters, how we came to this, it is okay. The bottom line is we had all our normal data. Based on normal data, we trained a model. This model, this is actually called a source modeling. This model contains all the properties of normal data. If you feed any new data X to this model will tell us how well it fits. This fitness it will calculate in the form of probability by using Gaussian probability density function. This is the inside it. So this contains information of normal data points, and gives probability of any data point being generated using this normal distribution. Even you can like you use some data set to train this Gaussian mixture model. Now you can go back to each of data points again and calculate their probability. Some of them will have high probability, some of them will have low probability. Low probability data points are anomaly data points. This is offline application. But when we do online application, we have unseen data. If we train our Gaussian mixture model on, let's take example of my simple intrusion detection in farms. I place a microphone in the farm. I record data for half an hour when nobody is walking. This is my normal farm data. I trained a Gaussian mixture model on that. And after training that model, I put that model in my mobile phone in the form of an app, and I start analyzing incoming audio data. Incoming audio data 1 second at a time. I take that data, I convert that into vector using some feature representation, and I feed it to my Gaussian mixture model that gives me its probability density. That gives me how well does it fit. If it fits well, the probability is high, it's normal data. If the probability is low, it is abnormal data. It works perfectly fine as long as there is no concept drift. There is concept drift. Suppose I trained my model in the morning. We had experimental results also for that. I trained my model in the morning at 7 a.m. तक मशीन वगैरह कुछ शुरू नहीं हुए थे, आसपास में कोई वाइब्रेशन नहीं था, बर्ड्स भी सो रहे थे, and there was no noise. But at 10 o'clock there is a lot of noise. So the normal distribution of my data has changed now. But model which I trained, GMM which I trained, mu1, mu2, mu3, sigma 1, sigma 2, sigma 3, still represent my data at 7 a.m. So I have to adapt my parameters of Gaussian mixture model in order to take care of this drift. So let's assume that there is only one Gaussian, and we have mu and sigma. How do we adapt that?
Excuse me, sir.
Yes.
Sir, what is the meaning of training of this GMM here in this contest? Training GMM means what? You said training of GMM.
Mhm. Training of GMM is actually the clustering. We take input data. So training of GMM is calculating these parameters mu1, mu2, mu3, sigma 1, sigma 2, sigma 3, w1, w2, w3. In order to get these parameters, there are two approaches. One approach is clustering, which we discussed. So you can divide data into different clusters. Once you have clusters, which you find using your k-means clustering algorithm, you can calculate mu, sigma for all, mu, sigma, and w for all these clusters, right? But the better approach of calculating GMM parameters is expectation maximization. Now, expectation maximization is a complicated, complex topic, which actually itself needs a couple of lectures to understand. So EM, expectation maximization, is other technique to obtain these parameters. So by GMM training, I meant you take the data and you apply some algorithms on it in order to obtain these parameters of three Gaussians, mu1, mu3, sigma 1, sigma 2, sigma 3. That is our GMM training. Did I answer your question?
Yes, sir. I got it.
Okay.
I got it, sir.
Okay. So
Thank you,
here
sir. Thank you very much.
we have mu and sigma and w, these three parameters, and we have to update these parameters in order to accommodate the concept drift. So first idea is that we can just drift the mean. I promised you that if you take probabilistic models, then our friends in mathematics department, they have given us some good tools to update the parameters of a probabilistic model. So for updating parameters of parameters of a Gaussian distribution, we have these nice equations. And these equations are also very interesting. So let's take this equation. I'll go one by one. Mu t is updated mean. So remember, I have parameters mu and sigma. Mainly these are updated. I have mu t. So again, I also I skipped one part here. In case of normal k-means clustering for anomaly detection, we have all data available. But here we are doing online anomaly detection, which means we have some initial data. With that initial data, we can start with some Gaussians, but majority of the data is coming online. Like we are labeling data, it is anomaly or normal, and at the same time we are training our model also. We are adapting our model also. So for each sample, our mu and sigma will change. And we expect that our mu will drift in this direction. Our mean will drift in this direction. Suppose I am able to represent my noise in audio in my normal noise sound as 0.3, and at 7 a.m. and at 11 a.m. it becomes 0.4. This should 0.4, 11 a.m. I expect that my model will change slowly from 0.3, 0.31, 0.32, 0.33, 0.34. It will drift and it will come to 0.4. So mu t will become 0.4 soon. And this equation is just for one sample, one individual sample. We are updating with each sample. So whenever we are getting new sample, that sample is classified as my background, then the samples, suppose it is in morning time, the sample's noise level will be 0.31, slightly more than 0.3. I want to update my mean. My mean will be 1 minus rho mu t minus 1. Mu t minus 1 is previous mean, like 0.3. Rho xt is the current sample value. Sample value will be 0.32 or 31. Why will it be 31? Because the noise level is increasing with time. So this xt, current sample, is slightly more than my mean value. This is like, this is xt here. This is xt. And here again, this is simple weighted sum. What is the weight? Rho is weight in our case. So with rho as weighted weighting coefficient, I can update my mean. I can update my variance also in the similar way with the equation. These equations are coming from mathematics. I have not derived these equations. I'm just using these equations for my audio analysis task. But the way this rho is calculated is more interesting. Rho is calculated with two components. One is alpha. Alpha is our learning rate. So alpha is something which is in your hand. You can tweak it. You realize that your normal data is drifting very fast. Concept drift is very speedy. Then you can update alpha very quickly. I mean, you can set alpha to a high value so that your mu t, this 0.3 to 0.4, will go very fast. But if you believe that it is slow, my background is changing slowly or my normal data is drifting slowly, then you can keep it low value. So this is application dependent. It comes from expert knowledge. But the second term is coming from data itself. The second term, neta, is neta is Gaussian function. minus mu whole square by 2 sigma square. Basically, sorry, it's very cluttered, but neta is the Gaussian density function. And neta is giving us probability density of xt. And this is probability, this curve is probability density curve. You can imagine that when this xt is close to mean, probability density is going to be high. If it is far away from mean, probability density is low. Effectively, my mu t will be updated less if xt, which is my current sample value, is far away from mean. You can you appreciate it? I mean, why would it update less when it is far from mean? If xt is very close to my mean value, then I'm more or less certain that this is actually normal data. I update with a large weight and I go close to 0.31. If xt is very far, let's say xt is somewhere here, somehow it is classified as normal data. Because it is classified as normal data, not anomaly, we are trying to update our mean. But because it is far from mean, there are fair chances that this is an anomaly. See, we are talking about probabilistic methods. All these methods are correct in majority of the cases, but they are not deterministic. You cannot guarantee that if our model is saying this is normal, this is indeed normal. It may be abnormal also. And the further this xt is from the mean value, more wrong we are, more uncertainty is there. So if we are not certain about concept drift, then we don't want to update our mu by large amount. So therefore, we are multiplying our learning rate with this density function, because any xt which is far from mu will have very low density. So these three equations we can use to update our parameters of GMM. So what we discussed was for unimodal class, but we may have bimodal normal class as well. So in case of bimodal normal class, we'll have two Gaussians. We'll have mu1, sigma 1, w1, mu2, sigma 2, and w2. Now again, if now you get any sample, let's say xt, any audio sample, you want to determine whether it is normal or anomaly. In that case, what you can do is you first calculate xt minus mu1. If this distance is less than or equal to sigma 1, then the point is somewhere here, and you say that it is normal data. If it is outside this, if it is somewhere here but you don't know, you try to calculate xt minus mu2 and see if this is less than 2 sigma 2. This is within this range. Then also you say that this is normal data, because right now my normal data is bimodal. There are two modes in my normal data. If any of these is true, then you say that data is normal. Otherwise, data is abnormal. Abnormal or anomaly. So you can relate it to our previous discussion. See, when we did not have time series data, when our method was not online, when we did not have concept drift, we used simple clustering. And any data that is far away from cluster centers, we took them as anomalies. But in case of online data, when there is concept drift, we cannot use clustering. We cannot use clustering in that sense. We actually use adaptive Gaussian mixture models where we keep updating mu and sigma, and therefore, because of this relation, this is also called online k-means clustering algorithm, this adaptive Gaussian mixture models. So far we are able to take care of intra-class drift when normal class is changing, but we may have inter-class drift also. कि किसी ने मोटर शुरू कर दिया, तो मोटर शुरू कर दिया, initially it should be flagged as anomaly, but later on it should be flagged as normal data, right? But this is normal sound now. So for doing that, we use more Gaussians. We use more Gaussians and we take xt input data samples. If it is close to any of these Gaussians, we update that Gaussian's parameters and we keep counting their number also. For all of these Gaussians, we have sigma, standard deviation. Remember, your standard deviation represents distortion in your cluster. For each of these Gaussians, we can keep counting number of samples which are matching each of these Gaussians that we have in weight. So again, we go back to our discussion of clustering algorithms. In clustering, the help of distortion and W, we were able to find out which cluster represents anomaly or which cluster represents normal data. So here also we calculate sigma, we calculate W, and depending on ratio of sigma by W, we can determine which of these Gaussians represent anomaly and which of these Gaussians represent normal data. And that's how we can do classification. So here, after implementing this multiple Gaussians, our algorithm is following. We take input sample xt, we find out कि वो कौन से Gaussian के पास में है, कौन से component के पास में है. For that component, we calculate sigma and W. We calculate sigma and W for rest of the components also. Whichever has highest sigma by W, that we label as anomaly. Okay, so in case of anomaly detection, this W is called persistence, and we cannot keep counting numbers because अगर हम count करते रहेंगे तो infinite हो जाएगा. So therefore we keep that in the form of weight and we keep updating this weight also. Okay, and this will be my last slide. In our group we use adaptive Gaussian mixture model, which I described just now for anomaly detection in audio, but we extensively explored other methods also. So one of my PhD students, he explored using Huffman codes for anomaly detection. You know, Huffman tree gives less bits to data which occurs more often, and it assigns larger number of bits to data which occurs very rarely. Those who know compression algorithms using Huffman coding, they understand this. So see what she did. She took all the audio data, she divided that into different samples, and for each sample, she calculated number of bits that we need in order to encode this data. And based on those number of bits, she found out whether the data represents anomaly or not. She in fact got good results. The paper is published in IEEE Census. Okay, so that will be all for audio anomaly detection from my side. I do understand that there are a lot of concepts which are packed together in this small duration of 2 hours. So if you happen to come to IIT Roper sometime for some of our courses, then we can discuss these in more detail. आप म्यूट में हैं, आपकी आवाज नहीं आ रही है।
Thank you, sir. So now we have question answer sessions. We have some questions. Participants also have some questions. So first, participants, you can ask the question. Sir will answer.
सर बाकी सब तो समझ में आ गया, ये लास्ट वाला सर हॉफमैन कोडिंग वाला थोड़ा ऊपर से निकल गया।
हाँ, हाफमैन आप हाफमैन कोडिंग आप जानते हैं पहले से?
Yes, sir.
सर लिटिल बिट।
हाँ, मतलब उसमें हाफमैन कोड का मेन कैरेक्टरिस्टिक ऐसा है कि जैसे आपको सिंबल्स को सेव करना है, जो सिंबल मोस्ट फ्रिक्वेंटली होता है उसको आप कम बिट्स में सेव करते हैं, और जो सिंबल कभी-कभी होता
बेसिकली
है
सर
उसको।
जो स्पीच का स्ट्रीम है, ऑडियो का स्ट्रीम है, उसका हमने चंक ले लिया, चंक का फीचर कैलकुलेट कर लिया,
हाँ जी, हाँ।
और उसके बाद जो है हॉफमैन कोडिंग का रोल आ जाता है।
हाँ, तो उसमें के बाद हम ये ऐसे जीएमएम जैसे क्लस्टर ही मेंटेन कर रहे हैं, वी कॉल देम कोड्स, और उन कोड्स का वेट जो है उसको हम प्रोबेबिलिटी की तरह ले रहे हैं, और उन वेट्स के बेसिस पे हम हफमैन ट्री बना रहे हैं कि वेट्स नॉर्मलाइज किया है, तो इफ इट इज नॉर्मलाइज देन वी कैन यूज दैट एज प्रोबेबिलिटी। उस प्रोबेबिलिटी के बेसिस पे हमने हफमैन ट्री बनाया है, तो फिर जब भी कोई नया डेटा पॉइंट आता है उसको हम इनकोड करने की कोशिश करते हैं। जो कोड होगा उसका प्रोबेबिलिटी बहुत कम होगा, वो हाफमैन ट्री में बहुत नीचे होगा, तब
ओके सर, ये
उसको ज्यादा बिट्स की जरूरत पड़ेगी, तो वो एनोमली होगा। मतलब ये अगेन this Huffman tree, using Huffman tree, adaptive Huffman tree for audio anomaly detection it is not a good method. We should not use it. It's very complex method. Out of our curiosity, we kept on doing research in this, that can we actually use a coding cost based method for anomaly detection, and we came up with some interesting findings, and the journal also accepted. So we cannot say that it is actually scalable and useful, but there are some interesting findings in this. Can we really apply Huffman codes for anomaly detection? Our answer is that it's very complex, but we can.
ओके सर, थैंक यू सर।
Sir, one question from my side, sir. I have seen concept drift for location. I have seen concept drift in context of time in your slides. But can we apply the concept drift for the change of speaker to identify the change in speaker?
So that is called abrupt concept change. That I thought of including that late, but because of the time limitation, I skipped that. That will be a different class of concept change, abrupt change. And for abrupt change, if you can anticipate in advance, then actually we develop models for the change detection only. In fact, we had exact same problem in our project कि जब टीचर और स्टूडेंट जब बात कर रहे हैं, जब वो चेंज कर रहे हैं तो हमें कैसे पता चलेगा? स्टूडेंट ने वो चेंज डिटेक्शन के लिए ही मॉडल बनाया था, वो उसे फिर हम उनके सेगमेंट्स में डिवाइड कर रहे हैं।
Okay, so one more question, some more questions are there. Sir, can we apply the efficient net in the speech recognition? Because I have seen it's a very successful model when the location or time changed.
Okay, so for that I will say, in order to apply efficient net, you have to use this spectrogram representation. You have, because efficient net is originally for images. So if you want to use efficient net, you convert into images, you convert into spectrogram, and actually you try. Because I have read research papers which claim that computer vision methods applied on spectrogram will not give good results for audio analysis tasks. But at the same time, I have seen many recent state-of-the-art papers which are converting audio into image using spectrogram technique and using these deep convolutional neural networks like efficient net in order to do the classification. But like you can use expert knowledge if the concept which you are trying to detect it's a combination of multiple frequencies and their location on spectrogram matters. Location with respect to each other, if it matters, then you can use spectrogram. Otherwise, this vision net. Otherwise, I think these days you can try this transformer-based method. Transformer-based methods are doing really, really good.
Yes. Sir, very simple question. The k-means clustering we generally use for the finding the clusters or to divide the data into the cluster. So can any other method we can use for this purpose, or which one is the best method for the clustering, sir?
Again, so this is for if you know the number of clusters, then k-means is best.
Okay.
Like if you know that there are two clusters, but in real life we don't know. If you don't know the number of clusters, then there are three clustering methods: agglomerative clustering, hierarchical clustering, and DB scan. So for anomaly detection, we almost always use DB scan method if we don't know the number of clusters. I did choose k-means clustering because it relates to my adaptive Gaussian mixture model later on, which is trying to take care of the concept drift. DB scan, it is hard to take care of the concept drift.
So last
So
question
there,
from my end. So just last
okay, there are a
question.
lot of audience which were waiting outside the door.
Yeah, sir,
So,
one question, सर मैं
evening
ऑलरेडी वन
time.
सर इसके लिए हम
नमस्ते
कौन
करते
से
हैं।
सर यूज कर सकते हैं सर करने
आप
के लिए
बताइए, आपकी
सर
आवाज ब्रेक हो रही है।
या सर हम लोग कौन कौन से टूल्स सर इसके लिए यूज कर सकते हैं सर कोई इम्प्लीमेंटेशन जब करना चाहेंगे सर कुछ टूल्स पे सर आप बताना है सर
स्किटलर्न लाइब्रेरी में सब कुछ है। ये जितने भी मैंने मेथड डिस्कस किए हैं, जेट स्कोर के लिए भी वहाँ पे लाइब्रेरीज हैं, क्लस्टरिंग के लिए भी लाइब्रेरीज हैं, और ईजीएमएम की लाइब्रेरीज नहीं है, वो आपको थोड़ा बहुत इम्प्लीमेंट करना पड़ेगा। फॉर इमेज बैकग्राउंड फोरग्राउंड डिटेक्शन ईजीएमएम की लाइब्रेरीज हैं जो ओपन सीवी लाइब्रेरी में अवेलेबल है पाइथन में। तो बाकी स्किटलर्न जो पैकेज है पाइथन का, उसमें सब कुछ है, सारे बाकी टूल्स।
थैंक यू सर
सर एक छोटा सा क्वेश्चन पूछना चाहूंगा सर।
जी सर बताइए।
सर ये गॉसियन मिक्सचर मॉडल में हमें कैसे आइडिया लगेगा कि कितने नंबर ऑफ गॉसियन रखने चाहिए?
अच्छा
सर क्वेश्चन से एक और मेरा क्वेश्चन भी है, दोनों इकट्ठे हो जाएंगे शायद, मुझे लग रहा है आंसर।
विशाल भी है, कौन क्वेश्चन बन रहा है?
हाँ सर, वन इज मल्टीवेरिएट क्वेश्चन, सेकंड इज मल्टीपल uses of univariate Gaussians. What is the difference between them?
See, univariate Gaussian and multivariate Gaussian, they are very straightforward. आपको univariate Gaussian में एक सिंबल स्केलर वैल्यू होती है, मल्टीवेरिएट में वेक्टर जाता है, उसमें स्टैंडर्ड डेविएशन होता है, उसमें कोवेरियंस मैट्रिक्स होता है। वो तो काफी सिंपल है, बट आप जब मल्टीपल गॉसियंस यूज करते हैं गॉसियन मिक्सचर मॉडल बनता है। मल्टीवेरिएट से गॉसियन मिक्सचर मॉडल नहीं बनता है। मल्टीवेरिएट के साथ यूनी मॉडल ही हो सकता है। और तो वो तो एक हो गया। और नंबर ऑफ गॉसियंस आपको कैसे पता लगाएंगे? तो अगर आपके पास ऑफलाइन डेटा है, जो कि इनिशियल क्लस्टरिंग में हमने यूज किया था, फिर तो आपको आप ये जो मैंने बताया एग्लोमरेटिव क्लस्टरिंग या हायरार्किकल क्लस्टरिंग आप यूज कर लीजिए, उससे आपको पता चल जाएगा कि कितने क्लस्टर होने चाहिए। आपको अप्रोक्सीमेट अंदाजा,
डिपेंडिंग ऑन नंबर क्लस्टर के उतने हम गॉसियन ले सकते हैं ना।
हाँ, आपको उतने गॉसियन लेने चाहिए।
But then the mixture model will be ready for solving the problem.
थैंक यू सर, थैंक यू वेरी मच।
Training use expectation maximization for Gaussian model.
एल्गोरिथम।
Yes.
यस सर, थैंक यू सर।
Imran, you raised the hand. Imran, ask your query.
Sorry, sir. My query was that yesterday I missed the attendance one.
No issue. Attendance is secondary. So
Yeah,
I think all the participants
FDP,
have asked
we
their
are-
question.
Sir, I do have a question, sir.
Please.
Okay,
Yeah,
Doctor.
sir, a very nice session, first of all. Thank you. And related to this, I need to know, sir, that is there any suggestion for the upcoming researcher of this field so that he or she can work on it? Some problems or say some idea that you can suggest that this is the best way to work on further. Thank you.
So I think I gave a hint in between as well, that this concept drift is a big challenge for people working in machine learning data analysis. So, for to handle concept drift, a new research area is emerging, and that research area is called continual learning. That's a fancy name. Effectively, they do the same thing. They are
Ji.
trying to give adaptive machine learning methods, which can be where parameters can change over time. So the continual learning is a upcoming research field, and second is for all data analysis tasks. If you focus on timeline, then you'll be able to find more interesting research problems. Like look at time series data instead of looking at samples. You can take for agriculture data analysis, you can take temperature, average temperature in the season. You can take the time series of season. So in case of time series, you have to profile the, how did it vary with each day. So many researchers have not explored this time series data analysis much. So that could be another direction.
And sir, sometimes there is a challenge that the data taken from some of these sites is not been considered as the authentic data. So, and can you suggest any solution to this, that this is the new site or this is the site by which we can have the authenticated data or from the government side data, so the researcher could not face this problem?
No, I actually cannot give any suggestion क्योंकि government side data हम आपको बता रहे हैं. For agriculture research, we went to this local panchayat office to get crop yield data. And they told us कि सर हम तो बैठ के ऐसे रजिस्टर में लिखते हैं, कोई किसानों से नहीं पूछता. तो डेटा, authentic data मिलना, it's very difficult. In fact, what we are doing, because we have a PhD students, we are collecting on our own. But for some data, we have these online stores like Kaggle. Don't recall any other. I mean, there are a lot of online dataset repositories.
Yeah,
Uh,
some
you can
repository,
do one thing,
CIP
like
repository.
those repositories, they have dataset challenge, algorithm challenge. Whichever repository has challenge, their data is authentic. Multiple people cannot implement code on some data if the data is not good. Kaggle has this leaderboard, so therefore Kaggle data is more or less good generally.
Yes. Thank you, sir. Most of the students are also preferring the Kaggle data nowadays, or till now, I can say.
Yeah, they do spend a lot of efforts in keeping the data clean.
Thank you, sir. Thank you.
Okay, sir, it's a good time to end the session. Thank you very much. Thank you, Dr. Mukesh, for this wonderful session. Really appreciate your expertise in the area of probabilistic models. Today we learned Gaussian mixture models in detail, K-mean clustering, many topics with mathematics, how they work. I really enjoyed the session. So this session will be very useful for us and our participants. I again thanks the Dr. Mukesh on the behalf of our participants. Thank you very much.
Thank you.
Dear participants, please fill the feedback form first. And tomorrow we will have one more session at the same time, 7 p.m. Expert will be from IIT Indore, Dr. Ram Bilas Pachori. So hopefully we will meet tomorrow on time. Thank you very much for your precious time you have given to us, and you have learned the new things here. Thank you very much again.
Thank you, Mukesh ji. Thank you, Vishal ji. Thank you very much.
Thank you.